So let's talk about something new today. So we were talking about complete sufficiency and how it's related to minimal sufficiency. And so we talked a lot about sufficient statistics, minimal sufficient statistic, complete minimal complete sufficient statistics, and so on. So the point now is we're going to do some statistical analysis in the sense of sufficiency is related to risk or statistical risk. So there are basically two results, one Rao-Blackwell, the other one Lehmann-Scheffé, that connects sufficiency back to risk. And so in order to state the first one, which is Rao-Blackwell, we need this idea of a convex loss function. And so if you remember the decision theoretic setting, we had a loss function. And then you applied this to your estimator or a statistic, and then you would get the risk. So this is the R, theta, and delta. So what we want to do is study this and the effect of sufficiency on this. But the particular result is a result about convex loss function. So we need to know what convex functions are. So how many people know what convex functions are? Okay, so what is a convex function? Maybe a good portion of people know.
The function that whenever you take 2 points and connect that 2 points at the line should go above the function.
Yes, great. Yeah, so like the picture is if I have a function, it's convex if and only if whenever I pick 2 points, let's say x and y here, and then connect them on the graph of the function and connect them, the graph of the function is below this line segment that connects the two. Okay, something like this is convex. It has to hold for all possible points. The other thing is something like that. So this is not convex because I can take these 2 points and the graph is neither above or below. It's concave if it's the other way around, but this one is neither convex or concave. So convex, not convex. And if you think about this definition, if you try to translate it into a formula, it's not hard to see that any point on this between x and y here is can be parameterized as lambda x. Let's say 1 minus lambda x plus 1 minus lambda y, where lambda varies in 0 to 1. So as I change lambda 0 to 1, I'm going to sweep all the points here. And so if you look at the generic point here, let's call this x lambda if you want, or I don't know, p lambda or something else. Maybe z lambda. It's a point in the middle, so this is z lambda. So this is going to be f of z lambda. This is going to be, it's not hard to see because that's a line that connects, this is f of y. This is f of x. So this thing is going to be lambda f of x plus 1 minus lambda f of y. So this definition is really saying lambda f of x plus 1 minus lambda f of y is above f of z lambda. So we call this z lambda. So that's this inequality here effectively captures that geometric picture. So this is on that line segment, and this is on the function. So the value of the function at that midpoint is below that line segment. So it's convex if and only if this holds. There are a lot of other equivalent characterizations, but people often start start off with this as a definition. Okay. Questions? So convex functions sort of go hand in hand with convex sets. So what is a convex set? Yeah, so it's like a convex set is I pick two like arbitrary points, connect them by line. That line segment is inside the set. This other set, for example, let's imagine like something like that. This is not convex because I can take 2 points and some part of that line sort of falls outside. So if you want to remember the connection, if a function is convex, if you look at the epigraph is anything above. So you look at this point, a generic point, and you continue this point all the way up. So anything above the function. If you look at the epigraph of the function, which is a set, that set is convex. So a function is convex if and only if this epigraph is a convex set. Okay. So epigraph is defined as the set of all like t and x such that t is above f of x. So this set is convex if and only the function is convex. So there's this intimate relation between convex sets and convex functions. There's also like a characterization. So if the function need not be differentiable, so there are a lot of non-smooth convex functions. It's like a very favorite of statisticians in this L1 type of function, something like that, absolute value of x. This is convex, but not differentiable at that point, 0. But if a function is differentiable, then it's convex if and only if it stays above the tangent line. So that's, if you like let these points approach each other, then you can see it's like equivalent to saying that the function stays above the tangent line. There are a lot of properties. So these functions have a lot of properties. A lot of interesting things happen when you try to optimize convex functions, or minimize basically convex functions over convex sets. So global minima can be achieved. Some classes of these problems can be solved fast. And there's a whole industry. So convex analysis, convex optimization, if you're interested. And a lot of this has uses in statistics. So they're quite easy to work with, not quite, but much easier than general functions. So they're well behaved. They can't have these like multiple local minima, for example, local maxima, something like that could go up and down. This doesn't happen for convex functions. So maybe we can come back to this. Even if the function is not convex, there is usually, like at least in finite dimensions, there is a supporting hyperplane. So I can pass a linear function such that the function is entirely above. So this is a very useful property. It doesn't happen for a general function, but convex function admits support, like supporting hyperplanes, or in this case, in 2D, it's like a linear. So a linear function such that defines a hyperplane or a half space. So it's a function entirely in one half. So this is very useful. Okay, any questions? A very short introduction to convex functions and convex sets. So we care about the loss functions that are convex in this action argument. Okay, so it has a loss function has 2 arguments. If it's convex in the action, we call it a convex loss function. So generic class are these LP loss functions. So like on R, theta minus A to the power of P, absolute value. So if P is bigger than or equal to 1, these are convex. If P is from 0 to 1, they're not convex. And if P is strictly bigger than 1, they're strictly convex. So strict convexity So what does the strict convexity mean? Yeah. Yeah, so this should be strict inequality, like lambda is strictly 0 to 1. At the endpoints, it's gonna match, but the way I wrote it, this inequality is trivial at lambda equals 0, 1, also in this function. But for any lambda strictly 0 to 1, we want, if this is strict, then you say strictly convex. So these differentiable smooth, like this function is strictly convex. Okay. This function, the L1, is not strictly convex because you can see here on this part, if I take these two and I connect them, so the graph of the function matches that line segment. So these functions that have flat pieces, right? They're not strictly convex. Okay, strict convexity is stronger than convexity. Because actually there is a notion called a strong convexity, which is even better, but we'll see whether we want it or not. So strict convexity is going to be useful. So L1 is not, for example, and this is an example of the L1 loss. So if you imagine this is A, if you think of the L, theta, and A being L, theta, and A being oh, this was not what I wanted to do. So L, theta, and A is like theta minus A. This would look like something at theta. You just shift that to theta. Okay, it's the shifted version of this. So the L1 loss is not strictly convex. Okay, sounds good. So why this is interesting from a statistical perspective? Many reasons, but a very interesting result called Jensen's inequality or Jensen's inequality tells you something about the expectation of a convex function. So if you have a convex random variable, sorry, a convex function in a set S, defined in a general set S, say this is Euclidean space, but could be more general, a random variable that takes values in S, what I've written here is concentrated on S. What it means is the probability that X belongs to S is 1. Okay, so it can take values. Actually, it's like it almost surely takes values in this. So the function has to be convex on where this random variable lives. Okay, so it can be potentially defined over a bigger area, but on S, on which this X is concentrated, it's convex. Okay, so that's what all we care about. And that the X is integrable. So the expectation of the absolute value of X is finite. Then this inequality holds. So F is convex, then expectation of F of X is bigger than or equal to F of expectation of X. Okay, how many people have seen this result? Okay, a couple of people. It's a very useful result. And there are different ways to remember it, but if you have a convex function, you pull out the expectation, it becomes bigger. If it's harder to remember, you can just remember the X squared, right? So if F of X, if it's X squared, then this is saying expectation of X squared is bigger than expectation of X squared, which is just saying that the variance is negative. So if you remember what the variance is, you remember the direction of this. Another way of seeing it is this is really what is happening on that line segment. This is the F at that. So this is really okay, let's do this. intuitively, this is a generalization of this phenomena. So what is this? This is f of expectation of x. What is this? This is expectation of f of x, right? In a particular case where x takes two values, little x, y with probability lambda with probability 1 minus lambda, you can see that the expectation of x is just, what is the expectation of x? Lambda x plus 1 minus lambda y. This is lambda f of x plus 1 minus lambda f of y. So when a random variable takes two values, Hansen just reduces to the definition of convexity, and then this is a very, let's say, interesting generalization. So you can have a general random variable. You have a distribution of mass, and then this inequality is the whole. So you can try to, for example, extend this to multiple points. So this is like a discrete variable that takes multiple values, xi with probabilities alpha I. So that's like a generalization, but this is even like much broader. So yeah.
And just to clarify, that's the expected value of the absolute value of the random variable in the proposition?
Yes, this, you mean this one?
Yeah.
Yes, yes. So that's the assumption that the expected value of absolute value is fine. But this is needed for this expectation to make sense. Okay, so if you remember, I've taken measure theory. In order for this to make sense, you need this. Okay. Sounds good. So I usually prove this, and the proof is there, but I'm going to skip it this time. The proof is really simple. As a consequence of that supporting hyperplane, you're welcome to read, since some people also know about this. Let's use it. And then there's this last piece here, that whenever you have an inequality, one question that you can ask is when equality holds. Okay, and the equality holds if and only if, if f is strictly convex. If f is strictly convex, then equality holds if and only if x is equal to its expectation almost surely, which means that x has to be a constant random variable. If x is not a constant random variable, then it's going to be strict for a strictly convex function. And it's not unbelievable because of this property. It doesn't hold for general convex functions because, for example, you can take f to be linear, the equality always holds. So, sounds good. This is one of the uses in probability or statistics, is this inequality. So let's see how we can use the equality questions. Okay, skip the proof. This is the result for all black holes. So suppose you have, so remember the decision theory framework. You have a decision rule, which is really an estimator that takes your x and outputs something about theta, an estimation of theta. You have the risk, and you have a loss. So loss, the value of the estimator is this, and then you take the expectation of the risk. So Rob Blackwell says if T is sufficient for a family, so we are working with a parametric family, T theta in omega, and delta x is a possibly randomized decision rule. I'm going to come back to what that means, but you can think of it as just your regular deterministic decision rule for now. And this loss is convex in the second argument for all theta. Okay. This holds on these three hold, then now Blackler essentially says that I can improve this estimator by conditioning on T. Okay, so you have a sufficient statistic, you have the decision rule, you condition the decision rule on T, you get either a better rule or a rule that is as good. Okay, so that's the idea. So if you take the eta of, define eta of T, which is going to be a function of t, as expectation of delta given t, a new estimator, then eta dominates delta. So the risk of eta is going to be less than or equal to the risk of delta for all theta. And if it happens that the loss is strictly convex, unless eta is actually equal to theta, eta is equal to delta, then the equality would be strict. So you have a strict domination. So this new eta would render delta inadmissible. So let me maybe repeat. So you have a sufficient statistic T. You have a candidate decision rule estimator. All Blackwell says when this happens, you just create a new estimator by conditioning on T, the sufficient statistic. You get a new estimator. There is a subtlety here that I'm going to talk about. But this new estimator, eta, is going to be an improvement in general. So the risk is going to be at least as good as the risk of delta for all theta. And if the loss is convex, and if this conditioning produces a new estimator, it's not identically equal to delta, then you get a strict domination. So delta is really inadmissible. There's a very interesting result. The proof is actually a very simple application of Jensen's inequality. It tells you that sufficiency is really capturing something statistical in the convex loss case, in that if you're not a function of a sufficient statistic, you can always improve the conditioning on it. Okay. Is the statement sort of clear? So so think of the conditional expectation as averaging in a sense. You had the projection viewpoint. Another way of viewing it is the average. You're averaging the randomness. It's really averaging is another viewpoint. So I'm averaging this delta x over values of t. So whatever, if there's variation in delta x, which doesn't come from t, I'm averaging out. So I'm going to reduce the noise because that part of variation is like irrelevant. Or you can think of it as projection. You're projecting onto the space of functions of t. You're going to get a function of t. So the caveat here, or like subtlety, is that if I do this projection, because I'm taking the expectation under t theta, this potentially depends on theta. So I should really write eta of t and theta. And then this wouldn't be an estimator. It's not a valid estimator. So why am I allowed to write it like that? And why do I actually get an estimator? So this is really, because t is a function of x, my claim is that eta will be a function of t only, so it's really just a function of x. There's no relation, like there's no dependence on theta. So it's a valid statistic. The statistic is any function of your data. Why is that true? This has come up in the past.
Taking the expectation, the table.
Yeah, so this is, if you go back to the theorem about complete sufficient statistic implying minimal sufficiency, or BASU, we use this. So the distribution of x given t does not depend on theta. So the conditional expectation here is working under the conditional distribution of x given t, and so produces something that doesn't depend on theta. So it doesn't matter under which of the p theta you do this, because t is sufficient. This is well-defined, the well-defined estimate. Okay, and that's the only place in this theorem that we're going to use sufficiency. interestingly. So eta is well defined. If you have followed my terminology, this means the way I wrote it doesn't depend on theta. So it's really well defined in the sense that I can write it as a function of t only. So if that's the case, then so I can apply Jensen, like Jensen conditional on t. So conditional expectation behave like expectation. So this result, for example, I can do something like that. Expectation of f of x given z is bigger than or equal to f of expectation of x given z. So I can condition everything on z, and it would be true, right? So conditional expectation is a form of expectation operator. So that's what we're going to do here. So if you stare at this inequality, that's really Jensen's inequality. So I'm having the expectation of theta delta t here, and I'm pulling the expectation out with convex function, and so it gets bigger. That's the Jensen's inequality. So this is really Jensen conditional on t, and so this by definition is really eta of t, right? So this is really the loss, L of theta and eta. This is the loss of theta. And so now I take expectation of both sides. So this is an inequality which is random, like random because t, this side is a function t, this side is also a function t. Now I take the expectation of both sides. Expectation is monotone. So I get expectation of L theta delta given t bigger than expectation of L theta eta. Okay. So what is this guy? That's the risk of eta. So what is this? All right. So this is some random variable. Power property. Or what they call smoothing. So this is going to be just the unconditional expectation of L theta and delta.
So the outside expectation is with respect to t.
Yeah, there's just one expectation operator, but yeah, this is really a function of t. You're taking the expectation of a random variable, which is a function of t, which is a function of x in the end. So everything is a function of x in the end. So what is this? This is the risk of delta. So we showed that the risk of delta on the other side is bigger than or equal to the risk of eta. A strict inequality holds if the loss is convex. Imagine here, if the loss is strictly convex, and eta of t is not equal to so under the Jensen, like conditional Jensen, so this should be constant. If I want the if the loss is strictly convex, this I can drop this inequality unless the speed of t is constant. Sorry, unless this is basically, if you want to say it's just it's easier to say. If x is equal to the expectation of x, in the conditional case, this means f of x would be equal to, sorry, x would be equal to the expectation of x given z. So if you apply it conditionally, unless this inequality holds almost surely, so this can be translated into this. Unless x is equal to the expectation of x given z, then the inequality would be strict. And so in this case, if the loss is strictly convex, unless yeah. um, Here, yeah, so this is our X here. This is our Z. Okay, so unless, so think of delta as X and this is as Z. So unless delta is equal to, that's X, equal to expectation of X given Z. So unless this happens, which is just eta. So unless delta is equal to eta, then this has to be strict. So I'll let you think about that implication, but without this, it should be fine. Yes.
Did we ever explicitly talk about the smoothing and the Dower property?
We did. Where we did talk about last week? Exactly in what context? A little bit, like you have to rewind a little bit back. So this conditional expectation as, here we go, as L2 projection, right? So the error has to be orthogonal to everything, in particular to the constant function. Right, conditional expectation is the best predictor, and in particular, it's orthogonal to any function of x, in particular, orthogonal to 1. And so when you write down error is orthogonal to 1, let's get this property that expectation of 1 is equal to the expectation of y. So go back to this. This is a consequence of the projection idea. It more generally holds, but this is called either smoothing property or averaging property or Tower property. Different people call it different things, but you're smoothing out. It's like a function of taking expectation generally smooths things out. So it's like smoothing, you get back the original expectation. But it's helpful to review. This is a very useful property of conditional expectation. Some people call it iterated expectation or like many different names. Okay. Smoothing property, iterated expectation, whatever you want to call it. So you take the conditional expectation, you take another expectation outside, you get back the original.
So you said that the estimator should be possibly random. So if it is not randomized, it will be equal.
No, possibly randomized is saying it's even more general than we're talking about. Like it holds for non-randomized decision rules. Right? What it's saying is that if I do randomization, so what do we mean by randomization? So what do you think what randomized decision rules mean? So a classical or like typical decision rule that we were talking about takes something from X and maps it to like the action space, or let's say, usually omega. So it maps something from the space of data to a space of parameters. A randomized decision rule gives you a probability, let's say. You can think of it as a probability kernel. So it's like, it tells you, so you can interpret this as not the parameter, but the probability distribution that you sample from, that would be your estimate of the parameter. So the easiest, there are different ways of doing it. For example, I can say it's like deterministic. You can say it, so a randomized rule could be something like that. You can view it as like a function of some external random. So it's like delta of x and u, where this u is like, for example, uniform. So I allow you to make your decision based on the data and an external independent source of randomness. Another way of viewing it is okay, this is just, at this point, it's deterministic. So either it's deterministic rule based on some extra sort of randomness, or you can view it as just as this, but this side is not, so delta of x in this view, delta of x gives you probability. Yes, you could have different decisions.
sampling is deterministic.
Sorry?
Sample mean would be deterministic. Yeah.
Sample mean is deterministic, yes. Sample mean is deterministic. Yeah, so you basically produce some let's see if I have like a better statement here. Yeah, I don't have it. But like, okay, so the different ways, this view is the easiest. Okay, so imagine I give you another source of randomness, you can flip a coin and based on X and U decide. So if you ignore this, it's random because even if I give you X, it's not completely determined. Or you can say, okay, delta X gives me some sort of, I'm gonna only specify, let's say, the probability that delta X belongs to some set A. So I'm gonna specify a distribution for delta X if you want. In any case, so the easiest thing is like imagine delta, okay, X maps to random variables in omega, okay? So for every observation, you give me a random variable, a random decision. So then why this works? Because everything goes through. So for example, when I take the expectation here, even if this is random, it's going to take care of the random. The average is over both the noise in X and also the extra randomness. So this is going to be really deterministic estimate. Because once I take the expectation, it's just going to be a function of T. And T is a function of X. So there's no randomness. So this conditioning removes the randomness. So for a randomized decision, we'll think of this as just a random variable. It's a random variable because of X, but like even conditional on X is a random variable. That's the easiest way to think about it. So what this is saying is that randomization does not help with convex loss functions. Why? I mean, because I can always do this conditioning and this removes the randomization. So Raoul Blackall is interesting in that as a consequence is that randomization for convex loss functions is not helpful. You can't do better by just adding your own version of noise into the output. Is that clear? Is it clear? Yeah.
Oh,
Yeah.
explain.
Yes. What do I mean by well-defined? Anyone can tell us? Yes.
That it can be written as a function.
As a function of T. Yeah, well-defined is when I write something like that, I'm saying I'm defining the function of T like this. So this is not correct unless this side does not depend on theta. Okay, that's what I'm saying. This definition is okay, because this side really doesn't depend on theta, only depends on this. It's really defining the function. Okay. I mean, theta, the way I define is well defined as a statistic. Okay, well defined as a statistic if you want. Or the way I wrote it, only a function of T, it's okay, correct. Does that make sense? If it bothers you, just replace it with, it is only a function of T. So this is really a valid estimator. Eta is really a valid estimator. Eta is a valid estimator. An estimator or a statistic, if you want, cannot depend on the unknown parameter. If T is not sufficient, potentially this will depend on theta, which I don't know. So it's not useful as an statistic or as an estimator.
That's because T is sufficient.
T is sufficient, yes. So this is really expectation of delta of X conditional on T and the distribution of X given. So this is really dependent, does not depend on theta by definition of sufficiency, right? Right? Yes.
So then I guess, could you remind us why we have that theta there? Is it just because the expectation changes
Right, generally you put the theta here. In this particular case, the output doesn't depend, but what I'm saying is I am taking the expectation under the distribution of x, which is p theta, okay? So whenever I put expectation here, sub theta, it means that I'm implicitly assuming x is distributed like p theta, one of these things in the family. Right, so the expectation operator associated with this probability distribution is this. So whenever I write it, I'm implicitly saying x is distributed like that. But then the result does not contain. So it's good to write it that way. Some people at some point drop the theta, but you should, I mean, this makes it more clear to keep track of. So if you don't write it, it looks okay. But really, there is something going on. So whenever you write it like this, it reminds you, oh, maybe we should depend on theta, then you think, no, it doesn't depend on theta, so you're fine. That's why we usually put it there to make sure. Good. Okay, so everyone now understands Rao-Blackwell, at least at the theoretical level. So here's like an example. So just to summarize, I give you a statistic, and I give you a sufficient statistic. There is an easy way of potentially improving it. If it's already not a function of that sufficient statistic, you can potentially improve it. So here's an example. Suppose you have xi's or iid 0 to theta. We know that the max is sufficient. We actually know it's complete sufficient. We proved that particular one probably 2 lectures ago. Or last lecture, I forgot. So that's sufficient. Imagine I take this potential estimator of theta. Sample mean, okay? Sample mean is not a good estimate of theta in this case. But I want to show you that it doesn't matter. Even if you start with a bad estimator, you can improve it. Both of them might not be good, but one is better than the other. So why in this case the sample mean is, there's a simple reason why this is really bad. There's a simple fix that you can do to make it at least reasonable without knowing Rao-Blackwell. Anyone can see why the sample mean is not a good estimate of theta. Yeah, okay, so this is like bias, right? So I think the expectation of this would be theta over 2. So better estimate would be twice this, right? So this is estimating the mean of the distribution theta over 2. So this is really a bad estimator. It's like off by a factor of 2, but I just want to show you that it's fine. So you start with any bad estimator or whatever estimator, you can sort of improve it. Of course, if you start with twice this, the procedure would produce twice, because that would be like expectation is linear, so 2 comes up. But let's start from this. So Rao-Blackwell says if I take the expectation of delta conditional on t, that particular t, it's going to strictly dominate delta. Why? Because it's strictly convex. Sorry, the loss is strict. I didn't tell you about the loss. Okay, so it's going to strictly dominate for any strictly convex loss. I'm not going to specify the loss. So pick a strictly convex loss function for analysis. For example, quadratic loss, the L2 loss. Rao-Blackwell says this is going to strictly dominate delta. Why? Because when I do the conditioning, this is going to be a function of max, only a function of t, and this is clearly not a function of the max. Okay, so I get something new. So eta would be different than delta, whatever I end up with. And so I know that if I start from this, take the expectation, this is going to be something, a new estimator, and it's strictly better for any convex loss function, particularly for quadratic loss. Okay, so let's do the procedure. So this procedure of conditioning and statistic is sometimes called Rao-Blackwellization, because I mean, conditioning is too simple. You want to like sound fancy, you say raw blackalization. We're gonna do raw blackalization, which is just conditioning on the sufficient statistic. And so all good, except that this is not easy to do, okay? In order to be able to calculate this, what do I need to do? I need to be able to, so in like theory, it's doable, but in practice, this is like delta of x1 up to xn, that's my x. And so I need to be able to take the expectation of this conditional on t, projection view, and things are like, they're good, but in practice, usually you have to figure out what the conditional distribution is. It's the easiest way. Not the easiest way, but like practically, it's going to be a simple example. I need to figure out what the conditional distribution of x1 up to xn given t is, or at least the sum given t is. And it's tricky. Because t is also like a non-trivial function of these. So I'm trying to figure out what I want to do is figure out the joint distribution of x1 up to xn, conditional on the maximum of x1 up to xn. If I have this distribution, then the mean of that distribution would be what I want. And if you have done the homework examples with continuous random variables, this conditioning is difficult, non-trivial. So how do we do this? Any ideas? So let me just maybe open up some new page here. So let's say x1 and x2, just two, even two is going to be interesting. And I want to find x1, x2 conditional on the max of x1, x2. And I'm going to even simplify. I let theta equal to b1 because if I divide x1 and x2 by theta, that would be uniform 0, 1. So let's just work with that, then we can figure out the general case easily by multiplying by theta. So x1 and x2 are uniform 0, 1. I want to figure out what the distribution x1, x2 given max is. So any ideas how to?
Can I start writing the formula for the conditional probability of x1 and x2 joined to be the maximum of these two?
If I wanted, so these are like continuous, so probably I should write something like x1 and x. You want something like this, or so how do we? It's tricky. The probability, are you talking about the PDF or PDF? So it turns out that this is like, so these have PDFs. The joint, you can have a PDF. So there is a PDF, probably distribution function for the joint. So joint distribution can be written as, I can write it like for joint, let's say Px1, x2, well, x1, x2. I can say this is 1 if little x1, x2 are in 0 to 1. If you want x1, x2 is in 0 to 1 squared, 0 otherwise. Okay, so there is a PDF, and if I want to show, like, plot it, I would do something like this. This is 0, 1, 0, 1, and then this would be just uniform 1 and this. So imagine it's just going to be a bivariate function, 1 here, 0 elsewhere. Yeah.
Isn't it sufficient to just evaluate like one of the conditional marginals?
We need actually the, in the end, I want like something like
Conditional is the same as a or like E here is sufficient.
this is T, right? Marginals would be x1 given t and x2 given t. I really, it's enough to calculate these. That's okay. The reason why it's enough is not rate sufficiency because I want to like compute the expectation, and expectation sort of sum comes out. So the conditional expectation of delta expectation goes in, you get the expectation xi given t. So if I manage to calculate, and by symmetry, they're all the same. So if I manage to calculate one of them, it's good enough. But this is also not easy. Not easy. It's easier to actually figure out what the joint is and then marginalize. The joint is easier than, maybe for you it's easy, I don't know, depending on how you do it, but I find it easier to look at this and then marginalize, but you'll see why this is tricky. And then you can go back and think about the marginals. So it's true that we really need the marginals, but I'm looking at the joint as a stepping stone to get there. So this is okay. The issue is when I condition on this distribution does not have a PDF respective of the Lebesgue measure. So it's neither continuous nor like discrete. It's like a singular distribution. The reason is once I condition, one of them has to be equal to t. Because we know that the maximum is t. So one of them has to be t. And so it's not all over the place. So for example, suppose I condition on max of x1 and x2 equal like a little t. I give you the max. I know that either x1 is equal to t, in which case x2 has to be less than t, or x2 is equal to t, in which case x1 has to be less than t. So if you think a little bit about this, the location of x1 and x2 is going to be limited on this plane. So it's not going to be on everywhere here. It's going to be a specific portion of this. Can anyone identify where x1 and x2 has to live in that case? Sorry? Yeah. Yeah, so it's not going to be past t because the max is t, so it's going to be at least this. And if you think about this, it's not going to be, it has to be like here. I'm just doing this first. Let theta equal 1, figure this out. Then we can do the theta. But let's say I'm assuming the x1, x2 are uniform 0 to 1 for now. That's just an assumption, okay? So if you think about this, it has to live here, right? On this side, x1 is the maximum. On this side, x2 is the maximum. That's the only choice, okay? The other one has to go, if x1 is the maximum, x2 can go from 0 to t. If x2 is the maximum, x1 can go from 0 to t. So it's really living this, it's a distribution that lives on this one-dimensional curve. And you can convince yourself that it has to be like uniform because the line is uniform. It's a uniform distribution on this piece. Okay, so the joint distribution is characterized as a uniform distribution on this curve. So that's how we describe it. Like, if you want to write it, you can try to write it, but this is the easiest way to see. Now, if I marginalize, what would happen? So if I marginalize, let's say you want to find the x1 given max x1 and x2 equal t. What I'm going to do is I'm going to draw all the mass. So that's really the distribution is just this. All the mass is here. So the mass of 1 is uniformly distributed over this once I condition. What I'm going to do is I'm going to drop down all this part here, drop down to 0, and also drop all this mass down to 0. So this mass that's like flat, this comes out as itself. This entire mass is like compressed into a point here. Okay, all of this mass gets to a point, and so you get a delta here. It's like a So with probability, so because of the uniform thing, 1/2 of the mass is here, 1/2 is here by symmetry. So I get a component which is uniform in 0 to 1/2, and I get like a point mass of 1/2 here, which contains all that mass that I lumped together down. So this, if you want to describe, you can say it's a mixture. 1/2 uniform 0 to t. This is t. Plus 1/2 delta of t. Delta here is a measure, not the. So this is the point mass. It's the distribution of a random variable that takes value t with probability 1. Okay, it's a mixture distribution, mixture of a continuous part and a discrete part. Does that make sense? So this point mass is easiest to see. Because there's like intuitively there's 1/2 chance that x1 is like the maximum. And in that case, it has to be t. Or like 1/2 that's not, then it can be uniform in 0 to t. Okay. So if you understand this, then you can figure out the n-dimensional case. So in the n-dimensional case, this picture would be more complicated. So let's say in 3-dimensional case, I first figure out the joint distribution of x1, x2, and x3 given the max. So we'll be living on like something like smaller piece here on the boundary of this. Then I'm going to flatten it. Let's say x1 and x2 given max x1, x2, x3 equal t. When I flatten it, the joint distribution of 2 given, you can see like 1/3 of the mass. So it's like 1/3 lives on this side, 1/3 on this side, 1/3 on this side. When I flatten, 1/3 comes out like uniform here. And this entire wall sort of comes down. So that would be 1/3 of the mass here and 1/3 of the mass here. It's like from 3 dimensions comes down. It's a little bit hard to visualize. But in any case, then I flatten it once more. I get this whole thing. So there's this 1/3 here, 1/3 here, 1/3 is uniformly distributed here. And then when I flatten it again, this 1/3 comes out to a point mass here. And this 1/3 and this 1/3 give me 2/3 uniform here. Okay, so you can figure out the joint distribution of like any number of components. Okay, so this is also interesting. It's like not, it's an interesting distribution, but once everything comes down, you get uniform 2/3, point mass 1/3. So in the n-dimensional case, so there's x1 given, max x1, x2, x3 equal to t. So in n-dimensional case, the final point is something like that. The maximum of x1, x2, xn equal to t. There's going to be 1/n point mass at t, and then plus 1 minus 1/n uniform in 0 to t. So, and this is another easy way of saying it is that this is the probability that x1 is equal to the max. It's like 1/n chance of being the max. And 1 minus n, otherwise free to be from 0 to t. That may be easier. I find this geometric picture more interesting, to be honest. Okay. So the difficulty is this idea that once you condition, the mass is like restricted because everything is a function of. So this max is a function of that. So once you condition, you restrict things to a certain set. So I'll let you think about the visualization for yourself. Once you understand this, you can visualize the n-dimensional case with strata tree, and then it will be sort of simple to see what happens. But that's the end result. Okay, so I have the conditional distribution that I wanted. Question? If you understand this, then how can I get from uniform 0 to 1 to uniform 0 to t? I multiply everything by theta, or theta, right? So this is scaled. So I multiply this by theta, the distribution would be equal to 0 to theta. Right, so nothing really changes. So this general case is, so you can see this doesn't depend on, this distribution does not depend on theta. Right, so nothing really changes. So this would be theta here. T can go all the way to theta, but the picture remains the same. So in the original family, what I get is the distribution of xi given t is 1 over n, a point mass at t. This is not the estimator, unfortunately, it's the same notation. This means a point mass at t. Okay. Delta t of A is really a measure. It's 1 if t belongs to A, 0 otherwise. And then 1 minus over n. So you can write it as an integral, or this is the easiest, the mixture notation. This is what I wrote. The meaning of this is the above. So it gives you the way to calculate the probability. But it's really a mixture distribution if you know what mixtures are. So the equivalent quantity is probably 1 over n. In that case, it's t, or 1 minus 1 over n that you draw in over 0. It's a mixture distribution. If that's the case, for mixtures, it's really easy. So you think about it. The expectation would be like the weighted average of the expectation of these two. So I'm completing the conditional expectation of, let's say, xi given t, it's just the expectation of this distribution, which would be like 1 over n times the expectation of this distribution, which is t. This is like constant and variable. And then 1 minus 1 over n times the expectation, which is t over 2. And then you like do the algebra, you get that. So that's the expectation of xi given t. And this is the same for all I, by symmetry or by the argument that we did. And so 1 over n summation xi, the expectation given t would be 1 over n summation I from 1 to n, expectation of xi given t. And this is the same for all of them. So you're averaging the same quantity, so you get the same thing. So that's really the final result. So that's our eta. Okay, so eta is really this. And you can see it's a function of t. It's sort of doing that 1 over 2 as well. Right? Actually, not that. Not right. So, worried about that. That's what. So this is sort of our Roble equalization. Questions so far? So Roble says the risk of this is going to be better. Let's say the quadratic risk, for example, is better than the original. And if you evaluate, I'll let you evaluate the variance. So the bias will be the same always. So when you do Roble equalization, this procedure, the bias is the same. Why is that? Bias is the expectation. So I think the expectation of this, like that power property is the same as the expectation of delta. So Roble equalization does not change the expectation, so it doesn't change the bias. So if you're looking at the quadratic loss, you know that the quadratic risk, the MSC basically has a decomposition bias squared plus the variance. So the bias doesn't change. So what Roble predicts is that the variance has to be better. The variance of the original is like 1 over n theta. So it's like the sample mean. So it's 1 over n, the variance of uniform 0 to theta. Right. So this is variance of 1 over n summation x1. So it's going to be like variance of one of them divided by n, which is like theta over 12. So that's the variance of a uniform distribution. So that's and that's something very strange. To calculate the variance of this, The variance of theta would be this prefactor squared times the variance of t. T is the maximum of a bunch of uniform random variables. So, it's a maximum of x1 to xn. So t over theta is the maximum of x1 over theta up to xn over theta. And because xi's are uniform 0 to theta, xi over theta would be uniform 0 to 1. And so t over theta is the maximum of a bunch of uniform IID uniform 0, 1 random variables. The distribution of this thing is known. It's an odd result of probability. So the order statistics of uniform are known to distributions. They're joint distribution, they're marginals. So this particular one, the maximum would be a beta distribution. So the distribution of this would be beta n and 1. And so if you want to look at the variance, so the variance of this guy would be 1 over theta squared. Or sorry, okay. So the variance of t would be variance of theta times this. So we theta squared times the variance of t over theta, which is a beta distribution. You look up the variance of the beta of Wikipedia. Okay, so this is the variance of beta n1. This is that prefactor squared. And this comes because of this normalization of it. So in the end, it's not hard to compute the variance of theta, and the variance of theta is after simplification comes down. So we compare. This is the variance of delta, this is the variance of eta. You can see this goes down like 1 over n squared. This goes down like 1 over n. So it's much faster. Goes down much faster. So we improved by a lot. If you instead, so delta is biased as we talked about. If you look at 2 delta, which is unbiased, the same story goes. So you end up with 2 times eta because expectation is linear. And then you compare 2 eta to 2 delta. So the same goes. So the variance would be just twice this, right? So this would be twice, sorry, 4 times that. The story goes the same. So the biases are the same, basically 0 in this case. The variances would be like 4 times. But the key is like this 1 over n squared versus 1 over n, which is a huge improvement. This is not what you usually expect to get. This is what you usually expect. So the variance of sample mean in general is like something over n, right? This is called the parametric rate. We'll see that. This is super parametric, so it's like much faster. And this is because you're looking at this maximum. And so, in any case, this is an example of all like, yeah.
So we describe
Yeah.
measures.
Yeah, so measure theory is good because it works.
Yes,
In
so
general.
how does some measures, like this go down? You have a direct measure. Yeah, of it uniform.
Yes, the rock. Yes, and then I'm adding them up. So how do
So
you?
that's adding.
Yes, measures are functions. So, right. What this really means is like, let's say I have mu1. It's a measure. And mu2 is a measure. Then mu1 plus mu2 is another measure. It has to be non-negative. I can't like subtract, but I can.
So is there a way? Yeah.
You don't have to see, you don't need CDS. So measures like you just have to specify what it does on a set. And so what it does is just does this. Very easy. It's like an addition of functions. Right? The measure assigned to a set is going to be the sum of the measures assigned.
So the probability of x1 being set A is equal to 1/2 of x measure plus 1/2.
So this is what I wrote here actually. So the probability that xi belongs to A is 1/2 this plus this times that's the probability under. Right. Yeah. You can scale measures by a positive factor and you can add them up. You're not guaranteed to get a probability measure unless you add up one. Right, so if you, okay, so this always produces a measure, but let's say if this was a probability measure, the probability measure, this is not going to be probability measure, it's just going to assign 2 to the whole space. But if mu1 is a probability measure and mu2 is a probability measure, let's say alpha times mu1 plus 1 minus alpha times mu2. If alpha is in 0 to 1, this is going to be a probability measure. Because in the end, the measure of the whole space would be alpha times 1 plus 1 minus alpha times 1. So a convex combination, this is called convex combination. Convex combination of 2 probability measures is a probability measure. The sum of 2 general measures is a general measure. So that's what's happening here. So I have these weights that add up to 1, right? And then I form a convex combination of 2 measures. One is a delta Dirac that T, other is and you can do it with any 2 probability measures. And probabilistic interpretation is that it's a mixture. So there is like a hidden variable. Whenever you have something like this, there's a latent variable that decides which way to go. In this case, the latent variable has a meaning. So it's like which of them is the maximum. Okay. So if you want, you can write it as let's just maybe do this quickly. So you can think xi given t and I, there's an I, which tells you whether the first one, so let's say x, I'm looking at xi, x1, and this is whether is 1 if x1 is the maximum. This is otherwise, okay? And based on this, if basically I is equal to 1, then this is a delta at t. If I is equal to 0, then this is uniform. 0 to t. Okay, and if you marginalize out this I, you get a mixture. We can come back. Just think about this example. If you have questions, let me know. So this is an example of a mixture distribution. And there's no easy way to represent it in general because there is one component which is discrete. There's one component which is continuous. So it's neither continuous with respect to the rate measure, neither or counting measure. So there's like very the case where just general measure theory works, but basic probability theory. I can't write a PDF for this alone or just a PMF, but I can describe it as a mixture of 2 components. One is discrete, the other is continuous. Okay. Sounds good. Okay. Thank you guys. I'll post these. Just think about it if you have questions. Yeah. Yeah.
We put expectation of that given T.
Yeah.
This is not a conditional expectation.
It is conditional expectation.
But it's not a delta given T. It's a big T equal to some small.
So that part you can set it equal to small t, then the whole thing is going to be a function of small t, but we can plug in the random t in there. Okay, so once you figure out the functional form.
I mean, is it related to the projection we were talking about?
It is related, but the projection viewpoint is not going to be that much helpful here. I have to get into the yeah, so this is going to be a projection. Projection is the abstract view. It's true, and it's helpful. But it's not going to help you. Maybe it helps. I haven't thought of it, but it doesn't help figure out what the functional form here is. You can probably use it to prove. So once you have this, you can prove it using the orthogonality. But usually, like if you remember basic problem, you set it equal to a fixed number, and then figure out the conditional distribution, integrate it, and then would be a function of that little number, and then just plug in the random t. So that would be the random variable. Sounds good. Okay, any more questions? Okay, thank you guys then. See you.